Hello and welcome to this discussion about dummy variables and multiple linear regression or MLR. The whole idea about dummy variables and linear regression is that we are able to use a dichotomous variable as part of a linear regression. So before we get started with that, I want to just make sure that we are all on the same page in terms of what linear regression looks like. And so in order to do that, I'm going to start off with simple linear regression. So for starters, when we have simple linear regression, we have a basic equation of y, or the outcome variable, is equal to beta 0 plus beta 1 times x1. And the beta 0 coefficient tells us where our y-intercept is. Our beta 1 variable tells us the slope of the relationship between x and y. The x variable is the predictor variable, and the y variable is the outcome variable. And I always love to draw that. And so here we have a scatter plot. And for this example, I'm just going to use an example where we are looking at birth weight as predicted by length of gestation. So if we think about how long a mother's pregnancy is, and so I'll call this length of gestation. Here's my birth weight. That's a W. You can imagine a situation where the longer the baby is in the mother, the bigger the baby gets. And so we have this kind of a relationship where length of gestation increases, and this is a continuous variable, and therefore birth weight goes up. And so we have some kind of like a linear relationship between those two variables. And this is generally what people think of when they think of linear regression, is that we have a continuous predictor, and we have a continuous outcome. And that's a nice basic relationship. So here we have length of gestation, and it increases, and as length of gestation increases, birth weight increases. So that's kind of a very concrete example. Now, I'm going to do something that we generally don't do, which is I'm going to create a linear regression with a dichotomous variable. So let's go back to our equation, and here we have our outcome variable, and let's let that equal to our y-intercept plus the slope times x1. Now that looks exactly identical to what we did before. We have an outcome variable, we have a y-intercept. This is, in other words, where the line crosses the y variable as where x equals 0. We also have a slope, in other words, basically rise over run. That gives us the angle of the line. And then we also have an x variable. But instead of having the same kind of x variable, let me just move that up a tiny bit, we're going to have a dichotomous variable. And what I mean by that is we're going to say for women who are smokers, we are going to call those 0. And for women who are non-smokers, we're going to call those a 1. I'm not sure if that's the same as it's coded in a data set, if you might be using something similar, but we'll just kind of go with that because then we'll end up with a positive correlation or a positive beta coefficient. So here we are still only looking at the relationship between two variables. So this really is an example of something I call we never do this. So don't get too hung up on the fact that we're really using this linear regression equation in a different way, but I'm doing this in the simple form so that I can show you what the graph looks like. And I think once you see what the graph looks like, this is going to really help. This variable here is still continuous, our continuous outcome. Let's say that that's still our birth weight variable. So let's go ahead and draw our relationship. Now the interesting thing that happens to this is because, I'm going to emphasize this right here, because our x variable is only has two possible values. I'm going to put those here. Here's my 0, here's my 1. What happens with those y variables, and let me make this a little easier to see, is that they all fall along. I'm trying to actually make this be a straight line, but I'm using my finger, so it's kind of a little bit jaggedy. Here's again, let's go ahead and put birth weight over here. Those are supposed to be evenly spaced, so this is still birth weight. So what this represents is that those mothers who are non-smokers, NS, versus smokers, SM. So here's my smokers, my non-smokers. My non-smokers, on average, have a higher birth weight, and that's exactly what we see kind of out in the real world. But what you see is you see an overlap between, like, let's pretend that these are kind of two distributions, and obviously in a real data set we'd have a lot more points than that, but for each of these distributions I have a middle point or a mean, and I could kind of follow that over to the birth weight, and here I have an average birth weight for the non-smokers. This wasn't intended to be at the top of the point, but you can kind of see the general idea. And what ends up happening then is that this beta coefficient right here represents, and I'm going to use black here just to make this really emphasized, that represents the difference between these. And I'll show you why. Let's just say that the difference there, oops, I need to be able to move this up a little bit to draw underneath it. So let's just say that the difference between those is 100 grams. And my birth weight, and I'm just kind of picking a number out of the air, my birth weight for smokers on average, this number right here is maybe 2,500, and the number for non-smokers right here is 2,600 in a particular hospital, maybe somewhere. And so this difference right here, the difference between the two, is equal to 100. And so what we end up with then in our equation is we end up, and I'll just kind of like draw it down here, I'll say birth weight is equal to 2,500 grams plus, and here's the difference between 2,500 and 2,600, plus 100 times x1. That's supposed to be a 1, sorry. Now, an interesting thing happens then when we apply these variables right here to this equation. As soon as we put a 0 in to this equation, that would be for smokers. So let's just put smokers. The birth weight, average birth weight, is equal to 2,500 plus 100 times 0. Well, what is anything times 0? It basically cancels out. So my smoker birth weight is 2,500. On the other hand, for my non-smokers, my birth weight is equal to 2,500 grams, of course, plus 100, and my coding says non-smoker is equal to 1. What is 100 times 1? Well, it's equal to 100. So what that ends up equaling is 2,600. And that's exactly what we saw on this graph up here, is we ended up with this difference right here between the two is equal to this beta coefficient for that equation. So anytime we put a dummy variable into the equation, the beta coefficient that goes with that dummy variable, the one that is dummy because it's just representing this difference between a 0 and a 1, coded as 0 and 1, that beta coefficient just represents how much bigger the group that's coded as a 1 is than the group that's coded as a 0. It represents how much does that go up when you add that particular group. Now, another way that we use dummy variables is that we use dummy variables for something that has 3 categories. And so let me go ahead and draw what that looks like for you. And again, I am only using the one variable in here, which is not something we generally do. But we have this basic equation, y is equal to our intercept plus beta 1 times x1 plus beta 2 times x2. And what this x1, oops, that's supposed to be an x, not a y, and x2. The x1 compares, just like up here, we were comparing 0, the 0 group to the 1 group, say smokers and non-smokers. Instead, let's do 3 hospitals. Let's say that we have our 3 hospitals, hospital, so we're actually drawing a line here. This is our new example. Hospital A, Hospital B, and Hospital C. So let's say that my x1 variable here is comparing Hospital A to Hospital C. I'm trying to think what's the easiest way to explain how this is going to work. Yeah, let's go ahead and go with Hospital A and C. And so Hospital C is going to be coded as a 0, and Hospital A is coded as a 1 in this case. So for this particular setup, C is a 0 and A is a 1. And then we also need to do a special coding for x2. And here we're going to compare Hospital C is a 0 and Hospital B is a 1. And so we have this special combination of variables so that we can always isolate just one of those different hospitals. The way that looks on, the graph then is, and I've probably done this in the way maybe that's confusing, so we could talk about this more, but let's say here we have Hospital C, and then we have Hospital A, and we have Hospital B. This just accentuates the fact that we don't have to have these in any particular order. We can pick any hospital to be our referent category. Whenever this equation over here on the left has a 0 and a 0 in it, that will be our Hospital C. If the equation over here on the left has a 1 and a 0, that is going to be Hospital A, because you can see anytime there's a 1 and a 0, that's going to be A. And then the third possibility is if we code this in such a way that this is a 0 and a 1, that's going to end up being your Hospital B. Now again, just like before, we're looking at birth weights over here on the left, and we're looking at the 3 different hospitals. And let's say Hospital C has some kind of higher birth weights. Hospital A is possibly kind of in the middle, and B is sort of in between. So each of these has, I'll just make this a little more accentuated, each of these ends up having kind of their own little normal distribution. So you can imagine this as being a little normal curve. And each of them also has a middle point of that curve. So we'll try to find the middle spot here. And what ends up happening is for Hospital A, what we want to end up knowing is how much different is that than what we're considering to be our baseline hospital, which is C. In other words, that beta coefficient here is going to be whatever that difference is between Hospital C and A. For the next one, we want to see what the difference is between Hospital C and B, and that would be this beta coefficient right here. And so just like we did in the previous situation where we only had 2 possible groups, smokers and non-smokers, it really just is representing the difference between your baseline group, and the other group that you're wanting to compare that to. So that is just a little summary of the beta coefficients in a linear regression that have to do with dummy variables. The way we really add all of this together is what a real multiple linear regression equation does is we end up having an equation that has our outcome variable, or in this case birth weight. We still have a y-intercept, and then we'll end up with possibly including the variable for length of gestation. We'll also include the variable, beta 2. We'll include the variable for smoker. We'll also include the 2 dummy variables. Let's see if I can fit them here. For the 3 different hospitals, and we kind of put those all together so that we can see how they all relate to each other as they're all impacting this this outcome variable simultaneously all together while they're both impacting each other and impacting this collectively on the outcome variable. So that's how we really use them in the real world. My example up above was kind of isolating each of the pieces of that equation. So hopefully that will help make the dummy variables a little bit more understandable. Thank you for joining me for that explanation.